here we are outside the Blanton Student Services Center, and one of the themes of our tour around SMU campus is the beautiful architecture here, and we're looking at different architectural elements. And so one of the things that's striking about this building are these beautiful, enormous columns that stand behind me. And there's this sort of classic question. It's a common question when you see a set of columns like this. Are the columns straight, or do they taper toward the top? Now, it kind of always looks like columns taper toward the top, but that's natural because things farther away always look smaller than they actually are, right? We know the moon looks like a tiny circle in the sky because it's so far away. So we know that the top of the column is far away from us, farther away than the base of the column here. So we expect it to look smaller, but on the other hand, did it really get smaller? Or is it only that effect of what's called foreshortening as it gets off into the distance? How could we possibly measure that? Well, it's not hard to measure the diameter of the column here at the base. So why don't we go ahead and do that? I can just measure the square plinth that it's on right across here. And that gives me 64 inches. And then I notice that the base of the column here is inset a little bit. So I just need to measure the horizontal distance to the actual edge of the column. To do that, I need to sight and know when I'm looking at the marking on the rule that's directly above the plinth. But fortunately, that's easy. I just need to look until I don't see the edge of the plinth anymore, so it goes straight down, and then I know I'm directly above it. So if I go here and I look left and right until I just don't see the side of the plinth, I get 10.5 inches. Now it's inset on both sides, so we lose 10.5 here, 10.5 there. So that's 21 in all. 64 minus 21, we know the diameter of this column is 43 inches at the base. But how am I going to measure the diameter of the column way up there in the air? I mean, I don't have levitation boots. I can't just go up and stretch my tape measure across up there. So again, I need to use something about the environment here that'll give me some clues so I can transfer a measurement I can make down here up there in the sky. So if I step back and I look at the building and I look at the facade, I'm looking for some kind of elements of the building that's going to give me a handle on dimensions up there. And I see that there are large square blocks that the top, the capital of the building here is made out of. And I can see this pillar is exactly centered between two of those square blocks. So if I knew the distance between the edges of the two square blocks, I would be able to get a handle on things. And luck is with me because I see that those square blocks match up with exactly these two lines of lights here. And then I can see those two lines of lights actually hit seams on the top of the building. And those seams on the top of the building are exactly aligned with the center lines of these windows, which are aligned with the windows below them, which are aligned with the windows below them. And bingo, now I'm down here at ground level. I can actually measure the distance from the center to the center of those two windows, and that will give me the distance between the two edges of these blocks up at the top of the column. So I'm going to go ahead and do that now, and I just want to measure from the center line of this window right there. Well, let me get the tape measure approximately right first. Okay, and so I'm just going to line this up with the center of the window right here and lay it out until I get to the center of this window here, and that's 120 inches, and we can feel pretty confident about that measurement because it's a nice round number, 10 feet from the center line of one window to the center line of the next. Okay, so let's go back to the base of the column and think about what good that does us. So we now know that this column is centered between the center line of those two windows, which are 120 inches apart, and it's 43 inches in diameter. So we know that down here it takes up just over a third of the space between the center lines of those two windows. We also know that there's two marks up above, the marks on the edges of the two square blocks there, that are also 120 inches apart. And so the question now becomes, up there at the top, is the top of that column more or less than a third of the distance between those two marks? Now you can actually eyeball it, and at this point I think you'd be pretty convinced that the column is actually less than a third of the distance between those two marks up there. But we don't have to rely just on our judgment and eyesight. We can also take a photograph. And what I've done in this photograph is I put a line segment that was right across the diameter of the column, which was easy because I got these nice marks on the center of the scrolls. And then I just moved that line segment over. This is an exact copy of that line segment moved over. And this is the center between the two blocks. So that if it was really a third of the distance, it'd be 1/3 here, 1/3 here, and 1/3 over here. But when I move that line segment over, so it matches up here, it falls short of this seam between the blocks here. So this column is less than 1/3 of the distance between here and its counterpart over here. And so we know that the column must have tapered as it went up to the top. And this is actually a common practice with columns, because as early as the Greek architects thousands of years ago, they noticed that by slightly tapering the columns, they actually look straighter and taller, and that gives a better impression of the building as you walk up to it. And we see that same technique being used by modern architects here on SMU campus thousands of years later.